I'll come back just to fill you in. The reason why I put Gay-Lussac in the middle is that where Boyle brings the pressure and the volume into a relationship, and Charles brings the volume and the temperature into a relationship, Gay-Lussac jumps from Boyle's law pressure to Charles's law temperature. It was just something funny that I figured out to help me to remember the relationship between the three different laws. Right, we ended off the previous presentation by saying that if we increase the volume of an enclosed gas means that the number of moles will be constant, then automatically, if the particles have more space to move in, they will exert less pressure. There will be less collisions, so less pressure. With Gay-Lussac, if you increase the temperature, you make the gas hotter, then the particles will move more vigorously, they will collide more often, so the pressure exerted by the gas will increase. With Charles, if you increase the temperature and you allow this gas to expand, then the volume of the gas will also increase. Now I want to take you to the graphs. From Boyle's law, we have an inverse proportionality. So if you increase the pressure, the volume will decrease. And taking you to basic mathematics, the graph is hyperbolic. So if you draw the graph of pressure against 1 over volume, being the inverse of volume, the graph will be linear. Okay, with Gay-Lussac, if you draw a graph of pressure against temperature, the two will be directly proportional. Similar with Charles, but now it's the volume against temperature. They are directly proportional. Right. So, just to conclude here, that for an ideal gas, the volume can be reduced to nothing, and then the pressure theoretically is extremely high. For an ideal gas, you can cool it down to 0 Kelvin, and the particles will have no pressure. For the ideal gas, you can cool it down to 0 Kelvin, and the volume of the gas will be 0. Okay, I hope you get that. Right. I'm going to look at Boyle's law by itself now. and I'm going to look at the graph of pressure against volume. And we know that it's a nice perfect hyperbola for the ideal gas. Now, the ideal gas particles volume is 0. Forces is 0. And you have elastic collisions. Now, we all know that for a real gas, if you compress it, it turns into a liquid. Why is that so? Is the big question. Now, if you think about it, the ideal gas will never turn into liquid. Never. So, if you have a real gas at a high temperature, the forces of attraction, if you have a real gas at a high pressure, the forces of attraction will make the particles cling together. So the real gas will liquefy. But I forgot about something. Boyle's law brings into relationship pressure and volume. But the real gas volume will never reduce to 0. So at very high temperature, at very high pressures, will the volume decrease like it should at high pressures? So our high pressures will be this part of the graph. This will be high pressure. The volume of a real gas will not decrease as expected from a gas. Now, Boyle's law is for an ideal gas. So the graph here will not go closer to the pressure axis. My line isn't very perfect, so let me redraw that line. So at high pressures, there is a deviation. The gas volume will not decrease as expected because the real gas particles contributes to the volume of the gas. I'll stop here and I will go on to the next video.